Hi guys, it's Parul here. So yeah, almost all of you asked for video demos and animation demos. So here are the demos. So this will be slightly different. First off, we will be using 64-bit architecture because my laptop does not have 32-bit libraries and I am not asked enough to install them. Plus, it will be slightly painful to just interact with 32-bit binaries on 64-bit in general. Even though they are supposed to be backward compatible, you have to do some stuff make sure that they are actually interpreted as 32-bit binaries. Anyway, so I will show you how function calls work with assemblies. Some of you commented that it's too abstract. Well, here is the raw memory. Enjoy. So I will first of all show you what the code is like. F1 main calls F1, F1 calls F2, F2 calls F3. That's it. Very simple. And finally a printf. So this will be good enough for how call stacks work. Once again, so there are a couple of options I've included here. First one is fno stack protector. This will be useful when you understand what canaries are. Canaries are a protection mechanism and they will come when we start overflowing stack to reach the return address exec stack. So all of you remember there are two parts in memory, code and stack. So there are some OS level protections which only allow instructions from code to be executed. We are changing that. It's not needed. Neither of them was needed, but I have put them just for completeness. O0 means no optimizations. G means debug symbols. There is a debug symbols would allow you to see the code lines. So these lines in the debugger. Backtrace.c and output is backtrace. Now enter. So backtrace. Do not ask me why my GDB looks like this. I won't tell you. So as you can see here, the code section. So this is what the -G flag enables. This is the assembly. This is the stack and some related memory. Okay. RBP and RSP. So we are not discussing main stack frame. It's built slightly different because there's stuff that's happening around main. There's a lot of stuff happening around main. In fact, if you scroll a little bit up, you can also see all the registers. Now most of them aren't relevant except for RAX maybe, which will have our return values every single time. So first of all, we zero it out. There are security reasons. There are reasons for why we zero it out. Long story short, the way main is set up, it has a return address, which is very problematic later on. Anyways, we'll come to all of this much later. That's not relevant. Right now, what's relevant is call stack. So right now, call hasn't been executed. Keep an eye out on the stack. RSP, RBP. Everything is 8 byte chunks now. Next, return address got pushed. As you can see, this is right after call F1. If you looked at it carefully, you can go back and see. I think this was 182. If I remember correctly, it is supposed to be 182. Now in F1 stack, F1 we create a stack frame, push RBP. This is RBP value, the previous RBP value, and you can see RBP creates a chain of itself, which is obvious because current RBP points to the RBP of the parent. Current RBP stores the RBP of the parent. Now stack frame created. This is the usable area, 16 bytes. This is obviously something we cannot use because parent RBP. Now once again, this time I don't think, yeah, this time it wasn't needed, but I think it's just there for security, like uniformity, I guess, or something. I am not entirely sure why this is there. The move EAX 0, 0, 0x0. Anyways, that's not relevant. What's relevant is the next call. I think I forgot to point out something in the previous stack frame. I'll point it out here. Stack frame is ready. Now see this. So RBP minus 0x4, that is 1, 2, 3, 4, 5, 6, 7, 8. This and 0x3, this is x equals 3. So this is being moved over there. So you can see this is the value of x. This is the return value. I'll tell you how I deduce that. Next we call F3. F3 is interesting. So we push RBP, move RBP to RSP. Now we do not sub. And the reason is we save two instructions this way. The move EAX, 0x0 and the sub RSP is 0x10. How that helps us is, since we know that F3 is the last in the chain, there is no further function call. The compiler knows. So it basically just assumes that there is no need to create a stack frame after a complete stack frame. I can remove some parts. Now, since optimization was 0, that's why it still did all this. If optimization was at a higher level, it would have pretty much optimized everything out. And then you wouldn't have understood anything, right? Now, mind you, RBP and RSC right now point to the same thing. So it's not being shown here, but I'll show you the memory, what the memory looks like. I will, to be precise, I will show you the next double word, the next 8 bytes. Now, so a word is 4 bytes, double word is 8 bytes. Just keep that in mind. X/1 xg dollar RBP minus 0x8. So as you can see, this is this is some garbage value. I have no idea what this is. Some garbage value mostly. So I will tell you what this command does. X means examine memory, and these are specifiers. 1 means the number of chunks that you want to get printed. So I wanted 1 chunk. X means the format. So it could be D, it could be something else also. X means hexadecimal, which is useful because it's like the memory. G means double word. G means double word. If it was W, it means word. And it stores the last used format. So see, I did not specify it, but it still prints a double word now. So this is useful. X is the bread and butter in GDB for you eventually. And this is where we pushed 5. Mind you, this is not a part of the stack frame because there is no stack frame, or not a proper one at the very least. Now we move this value to EAX because EAX carries the return value, if you all remember. So EAX, if you go up, EAX has 0, RAX has 0x5. We pushed it to EAX because we'll take the value from EAX, and the value itself was 4 bytes, so we don't need the entire RAX. So this way we can store 2 values in EAX if needed. Now we pop RBP. See, RSP shifted up and RBP went back to its original position. And now RSP points to the return address, which is why ret just reads from RSP. Ret. Now see, this is the fun part. We take the return value and store it in RBP minus 0x8. So this was already storing 3, which was the first value. Now we will store the return value, which is, I forgot, 5. So 5 was the return value and 3. Now we do some funky mathematics. We load 3 to EDX, 5 to EAX. So this is in EAX now. This is in EDX now. For those of you who wanted to see arithmetic. Now we add. So now EAX will have 8. See, once again, since 4 bytes, we don't care about the upper 4 bytes of the register. We do a leave. A leave is a pop. So a leave is basically move RSP to RBP and pop RBP value. It's happening at the same time. So yeah, RSP got moved to R. If you want, you can rewind the video a little bit and see this was the value above RBP. Since we moved RSP to RBP and RBP was below this, We first moved RSP to RBP, then we popped RBP. So RSP was first 8 by 8 bytes below this, so like somewhere here. Then that also got popped, so RBP moved here and RSP is here now. Now once again, this points to the next instruction. So ret just assumes that this is where you have to return ret. Once again, the same business. We move the return value to RBP minus 0x8. So here we move 2 to EDX, 8 to EX, add. Now we'll have a, yeah, RX has 0xa, which is 10 in hexadecimal. We do a leave again. So after this, RSP will be here and RBP will be to here. Side. Yep. And ret will pop this off and RIP will go back to wherever it was, which is here. Now the rest of the instructions are mostly relevant because we're back in main, but might as well just show you. Some fancy stuff is going to happen here and it will be interesting. So we take the return value, store it in RBP minus 0x4, which is here. So this is the return value. Initially it was some garbage value. I have no idea why it was there and why this specific value was there. It was just there. Don't ask me why. Next, we move this value. So this got moved to EAX right now. So RAX has 0xa. So 10. RAX has 10. Now we move this to ESI. ESI, if you remember, is the start index register, which is used for string manipulations. If you go back to, I think, second lecture card recording, I mentioned RSI and RDI. ESI and EDI are just 32-bit variants of that. So we move EAX value over there, and this RIP minus 0xe4e. Let's print this. Okay, I'll do an x/s now. So now f, what f does is interprets it as an ASCII string. So $RIP plus 0xe4e khali. I have no idea why this is empty. It wasn't supposed to be ideally. Okay, let's see. Anyways, so just let me inspect the memory once more. This is very sus. Okay, interesting. It's 0. Let's see. Okay, I can't make anything out of this. This doesn't look like an ASCII string either. So we'll just continue. So now RDI. We'll see what the contents of RDI are. These are the contents of RDI, and this was exactly the string we printed. Very weird. Very weird. Ideally, the way printf works is it has arguments in the two registers RSI and RDI. Now I have no, maybe I'm forgetting, but like I don't know what's happening here exactly, so just skip it. So we just continue. In any case, it prints 10 for you. Ta-da! So I hope this was clear with the memory. Now for those of you who said it's abstract, well, I presented to you the memory. There's nothing more I can do now. I can't show you the processors because like I need a microscope. You need a microscope. We don't have a microscope. So yeah, this was for stack frames. I guess I will be dropping another video for how to overflow buffers, basic buffers at the very least.